The objective of this part of the course is to look at how you analyse designs and processes with a view to reducing risk and reliability. The objective is to eliminate failures or to reduce the risk of failures. If you do have a failure, to minimise the risk of a catastrophic effect, and also to minimise the effects of catastrophic failures of components. Firstly, reliability. Reliability assumes that the initial performance is greater than the desired performance. If your initial performance doesn't exceed what you desire, then your design has failed immediately. Failure is then defined as being when the performance drops below the desired performance. So what do we mean by failure? It could mean a lack of function. That is, the thing doesn't work. It could mean that the manufacturing tolerances become too wide, and so that the component fails. It could mean that the performance of a device, the power output for example, is not as good as we would have expected, or we would like. We're going to look at two ways of assessing the risk. The first is failure mode and effect analysis. This considers individual components in the design. It looks at the different ways in which the component can fail. You try to do an analysis to identify all the different ways in which a component could fail, and then look at how that failure affects the performance of the system and the whole design overall. So we're starting with the individual components with failure mode and effect analysis, and working towards what an individual failure will do to the performance of the design. Fault tree analysis looks at it from the other end. It looks at the possible ways in which a device can fail, and then it identifies what combinations of events are required to produce a failure. If you can put a statistical value to these combination of events, then of each of these events, you can then add them together to make an estimate of how reliable your design is going to be. Where do we get the information? Well, the best way of getting the information is from direct experience. Full-scale testing, test to destruction. These all give us the experience and the statistical information to enable us to do an accurate risk assessment. However, full-scale testing and test to destruction are quite costly because you're wrecking something in the process. So experience, directly obtained, is the most accurate. The alternative is to use tests, simulation and confirmation tests. If you test an element, then that's cheaper than testing the whole. You take an individual component and you flex it to see how long it will last before it will break. However, the further you are away from the complete item, the less valid it is. If you look in the other item when we're talking about wear-related failure and the non-age related failure, the more components you have, the less an individual component has an influence on the overall failure. Also, the results that you have are being taken increasingly out of context. The final way of looking at it is analysis. This is where you look at the design and you make an estimate of what the risks are going to be. It's undoubtedly the least accurate because you're relying on people's expertise and experience. But it can direct testing to make direct testing more effective. So, first we'll look at failure mode and effect analysis, also known as FMEA. FMEA can be applied to planning, but we're going to look at it as it's applied to design and how it's applied to the process. You can also use FMEA or FMECA for failure mode, effect and criticality analysis to look at the impact of poor maintenance on the risk and reliability of a plant. FMEA consists of specifying for each component a failure mode. How the component can fail. Components can fail in multiple ways. They can buckle, they can bend, they can corrode, they can be overstressed. Each failure could have more than one effect. You look at what caused the failure and then look at what effect does it have on the system. And having done that, you then look at what needs to be done to reduce the effect or reduce the risk. Because it's an analytically based technique, the success of FMEA depends on the expertise of the analyst. It also depends on the management commitment to actually implement what the analyst decides. Design FMEA tries to identify inadequacies in the design. It assumes all the parts are correctly manufactured. It will only consider problems associated with the design or the materials specified in the design. So this restricts the categories of potential failures. The first one is you're specifying in your design a tolerance which is beyond the capability of the process that you're using to manufacture it. So this will produce a failure. You've asked for a tolerance which is not attainable. An obvious failure is if it doesn't meet the customer's expectation, or if it doesn't last long enough, or if it fails totally when in service. One of the impacts you have to consider is what the impact of corrosion will be on the life of the components. You also have to consider reasonably foreseeable customer misuse. If you're designing instruments that go around a process plant and you're having those installed, then you have to design them in such a way that if somebody decides they need to use them as a footrest to get up to reach something higher up, then it won't have any undesirable effect on the instruments inside them. If you look on computer systems, you will see ruggedized industrial units. That's precisely why they're ruggedized. The other possibility with the design FMEA is if the thing you design won't fit in with the customer's system. This slide shows a design FMEA. The component is placed in the column on the left hand side with an identification number, partly obscured in this transcript from the original. Its function is then described. In this case, we're looking at an engine bracket, and its objective is to provide engine support at the front. Then we identify the different ways in which it can fail. Well, one way in which it could fail is that it buckles. If it fails, the effect of the failure is to cause the engine to drop. And if the engine drops, the cooling fan goes into the radiator. Why might this failure occur? You have the cause of failure. Well, it could be that we've not correctly specified the material thickness. How do we ensure that we've correctly set the stress levels? Well, we've done an analysis and we have a stress report to show that we've done the analysis. So then we estimate what its current status is. We first estimate out of 10 what's the likelihood that this will occur. Well, we think this is going to be quite low, so we've estimated 3 out of 10. Then we estimate what's the severity. Well, if it does occur, the severity is 8, because it's quite a catastrophic event. And then we've looked at the chance of being detected. Well, if it does fail and the severity is 8, we will detect it. So if we multiply these 3 numbers together, we get a risk priority number of 72. The other thing that could happen is that the service loads are in excess of the design loads. This will cause a similar failure. Now, we haven't established what the service failures are, so the occurrence is 4, that might happen. The severity is going to be the same, but our risk of realising whether we have service loads in excess of the design loads is very high. So the risk priority number for this is 288. The other way in which the bracket can fail is corrosion. Corrosion causes a gradual loss of strength and it leads to structural failure. The failure is caused by inadequate protection. So at the moment we use a protective treatment against salt and spray tests. The occurrence of this likelihood is 2. Severity is still the same. The chance of us getting this wrong is also 2. So the risk priority number of this is 32. So if we were looking at this design, the area that we need to pay immediate attention to is finding out what the service loads are likely to be on this component. This slide specifies how we calculated the risk priority number, much as I described when we were looking at the last layer. You have occurrence, the severity, the detection, the risk that we've got it wrong and we've not noticed that we've made a mistake, and that multiplied together, these give us the risk priority number. So, what do we do to improve the position? If we want to improve the risk of failing, we carry out tests to verify the stresses are as per the report that we've done on the component. The tests prove that that it has adequate static strength. Therefore, the likelihood of a failure occurring is now reduced to 2, and the chance of us not having missed that it might fail is reduced to 2. So our risk priority number drops to 32. The one which we had most importance by, or the highest risk priority number, was the service loads in excess of design loads. So we need to verify this by road load data. Once we have the road load data, we can confirm that whether the design loads are satisfactory. If we've confirmed that, then the occurrence will drop to 2. The risk of us being wrong has dropped to 3, and therefore our risk priority number has dropped to 48. The final bit is about the corrosion. After we've done laboratory tests and road tests to make sure that that the corrosion is as we expected, then the occurrence is still likely to be 2 and the detectability is still likely to be 2. So actually we haven't really made any improvement in that part of the design. Process FMEA looks at problems in production that can cause the device to fail. It assumes the product design is correct. It only considers mistakes and errors that can occur during the manufacturing process. The sort of thing that it looks at is it looks at the specification of the materials that are being purchased for the job, the machine setting, how machining and assembling can affect it, what components can be damaged during handling, what errors can be made during the inspection and approval process, and finally what errors can occur in dispatch. Even once the component's been made and it's being sent on to another part of the country, an accident in the dispatch process can leave the component unserviceable. Typical failures can be the provision of incorrect material. One example is in aircraft bolts for light commercial aircraft. Because of the way in which the system was set up, it was possible to use the wrong material to manufacture high tensile bolts. In fact, the high tensile bolts were not made out of high tensile steel. You can look at equipment errors. You can look at mistakes that the operator makes. You can look at problems of contamination. If you're looking at designing circuits, failures due to contamination, where the circuits don't become, the printed circuits for example, don't become complete or the resistance becomes wrong, is an issue. It can also look at problems of handling, when things like threads are damaged during production. So again, we're going to look at this bracket which is holding the engine. What processes do we have to perform on this bracket? Well, one of the processes we have to do is we have to drill some holes to take the bolts. What happens if we drill the holes out of position? Well, then the engine mounting can't be assembled onto the engine. The failure is caused by an incorrect location in the drill fixture. Currently it relies on operator inspection. So the risk of it occurring is 5, the severity is 7, and the risk of it of not being detected is 6. This gives us a risk priority of 210. So it's quite a risky part of the production process. Another problem with drilling holes is they might be undersized. If they're undersized, you can't put the bolts through, so you can't assemble the engine. The cause of failure is the use of the incorrect drill size. The current controls rely on the operator to inspect and use a plug gauge to check that the hole produced is the right size. So the occurrence possibility of it happening is 3, severity is quite high, 6, but the chance of us detecting it is 1. So the risk priority is only 18. The other issue, the forming of the bracket, we might actually use the incorrect grade of material. If we use the incorrect grade of material, we have a structural failure. At the moment, the potential failure is caused by poor raw material identification, and the operator is required to know where the different materials are. So the possibility of this happening is quite high, the severity is quite high, and the chance of us getting it wrong is quite high. So this is the biggest issue that we have. So how can we adjust these things? Well, in the first case, the drilling of the holes in the wrong place, if we use a positive location on the fixture and a final acceptance gauge, then we know that the holes are in the right place and of the right size. We reduce the risk of occurrence down to 2, the severity is still the same, and the risk of detection has dropped quite significantly. So we know that we have a good component, so the risk priority number has dropped to 28. If we need to look at the drilled holes for the right size, a first off check with the use of an acceptance gauge will produce a minor improvement, reducing our occurrence risk down to 2, reduce our risk priority down to 12. The most important thing is identifying the raw material location and the racks and colour coding the material. If we implement these actions, the chances of us using the wrong material drop to 2. It's very difficult to detect whether you've used the wrong material after the component is made, so that still remains quite high, but the actual risk priority number has dropped. So to summarise, design or process FMEA look at the function or the process, they look at the modes of failure, they look at the effects, they look at the cause, they look at how it's controlled at the moment, and the current status. On the basis of that, we look at how we can improve things, we identify what action could be taken, and then we revise the status. So again, we're going to look at this bracket, which is holding the engine. What processes do we have to perform on this bracket? Well, one of the processes we have to do is we have to drill some holes to take the bolts. What happens if we drill the holes out of position? Well, then the engine mounting can't be assembled onto the engine. The failure is caused by an incorrect location in the drill fixture. Currently it relies on operator inspection. So the risk of it occurring is 5, the severity is 7, and the risk of it of not being detected is 6. This gives us a risk priority of 210. So it's quite a risky part of the production process. Another problem with drilling holes is they might be undersized. If they're undersized, you can't put the bolts through, so you can't assemble the engine. The cause of failure is the use of the incorrect drill size. The current controls rely on the operator to inspect and use a plug gauge to check that the hole produced is the right size. So the occurrence possibility of it happening is 3, severity is quite high, 6, but the chance of us detecting it is 1. So the risk priority is only 18. The other issue, the forming of the bracket, we might actually use the incorrect grade of material. If we use the incorrect grade of material, we have a structural failure. At the moment, the potential failure is caused by poor raw material identification, and the operator is required to know where the different materials are. So the possibility of this happening is quite high, the severity is quite high, and the chance of us getting it wrong is quite high. So this is the biggest issue that we have. Fault tree analysis looks at undesired events. It's a way of looking at hazards and working backwards to develop a list of causes and the origins of failure. This can be used with probability data to assess risk. So we have here a way in which we can mathematically look, based on understanding the risks of potential failures, to estimate what the likelihood is of a hazardous situation occurring. A fault tree is very much like a logic diagram. It has AND events where everything below the AND event must occur for the undesirable event at the top to occur, or an OR gate where at least one of the events below must occur for the undesirable event to occur. So let's look at an example of an FTA of a brake. If the brake fails, you can't stop. The first thing you look at is an OR gate. These are the things below this that if they occur, any one of them by themselves is enough to call a failure of the brake. If the master cylinder fails, if there's low brake fluid, if there's worn pads, all of these will cause it to fail. Also, a fluid leak will cause the brake to fail. For the fluid leak to occur, you can have a broken pipe, you could have a loose bleed screw, or a leaking cylinder. So these are all OR situations. Any of those that occurs, you get a fluid leak. Because you've got a fluid leak, you can't stop. An example of an AND gate is if the lever which causes the handbrake to come off won't retract. Well, there are several ways in which that can occur. If you don't have any lubricant and you have weak springs, then the lever won't retract. This is more of a problem if you do work on automobiles when you've got drum brakes. So, what have we looked at? We have looked at failure mode and effect analysis. This is where we look at the failure of individual components and how they impact on the performance of the design. We've done it for processes and we've done it for the design itself. And now we've looked at fault tree analysis. This looks at the undesirable event and looks at how you can add the statistics together to make an estimate of whether the undesirable event will occur.